Hello and welcome to this video on how to fit a growth curve model in Mplus when you have individually varying times of observations. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. On Tuesdays I usually talk about an analysis in the Mplus software, and on Thursdays I present more general issues in multivariate statistical analysis, including structural equation modeling, factor analysis, multi-level analysis, and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional free resources, including a link to my free weekly statistics newsletter, as well as courses that I offer through QuantFish. In this video, I want to show you how you can fit growth curve models in the Mplus software when you have individually varying times of observations, meaning when the distances between the measurement occasions are not the same for all individuals, and or when they also differ within the same people. So when you have very diverse times of measurement for different people, then how do you deal with that in growth curve models? The easiest case, of course, with growth curve models is that everybody has measurements at the exact same time, and also that the times are equally spaced. That's, so say, the easiest scenario, which we then which makes it very easy for us to specify, for example, a linear growth curve model where we can then simply fit the loadings on the slope factor to 0, 1, 2, 3, and so on for assuming linear growth. And so, but that may not always be the case. Sometimes we cannot have everybody take the test or questionnaire at exactly the same time point. Perhaps people are randomly prompted on their smartphone to respond to a questionnaire at random times during the day, and so there's maybe vast variety in terms of when people provide their scores, but you have the information about the times of observation and can include them in your data. And then Mplus has an option that is called T-scores that allows you to take those varying times of observations into account. So let's look into this and let's see how Mplus can handle this. I have an example here where in my data file that is named tscores.dat, I do have individually varying times of observations for 3 measurement occasions. And so in this data set, I have my 3 outcome variables that represent the repeated measures or the repeated scores across time. For example, repeatedly measured anxiety scores, let's say, or memory scores or something like that. And so y1, y2, and y3 then represent the same variable but measured at 3 different time points. Furthermore, in this data set, I have 3 variables that are labeled T1, T2, and T3, and those are the time score variables. So those variables indicate for each individual when exactly the first, second, or third time point took place. So it gives the exact time metric, so say for each of the 3 time points, and so those are included as separate columns in this wide format longitudinal data set. So let's take a look at that data set so that we can get a better feel for what this looks like. And so I have this data set open here as well, tscores.dat, and so you can see the first 3 time points are whatever scores we measured. So this first column would represent the scores on the outcome variable at time 1, and then the second column is the same variable at time 2, and the third column is again this variable measured at the third time point. And then we have the 3 time variables where you can see that the first time point was the same for everybody. So 0 indicates the first measurement occasion, and you can see that that did not differ between individuals. Everybody started at the same time point. This need not be the case. So you can also have different starting points for different individuals. Next, you can see that the second time point differed between individuals. So the first individual had a second time point that took place 1.127392 units of time later compared to time point 1. So whatever that is, so that could be hours or days or minutes or whatever. So say your time your units of time are, your time metric. And so you can see that that was not exactly 1, but 1.12 something. So there is this, so say, imbalance between the first and the second time point, and then versus the third time point as well, which took place 2.41 something units of time later compared to the first time point. And you can see that the second individual, for example, had the second time point recorded at a different time. So that was 1.20 units of time after the first time point, and then the third time point took place 2.02 units of time, for example 2.02 hours or so, or days after the first measurement occasion. And so this then takes this into account, the individually varying times of observation. And now when we go back to our syntax, you can see that then in Mplus the time scores have a special function, so they are listed under this tscores subcommand in the variable command to indicate that that's the variables that allow us to take the metric of time into account. Next, we specify analysis type equals random for this type of analysis, and in the model command we define our intercept and slope factors by using the special Mplus syntax for growth curve models that uses this vertical bar symbol here. And then the first factor that is listed or labeled before this vertical bar symbol will automatically be the intercept factor, so a random intercept factor will be included in the model, and the second factor is automatically in Mplus a linear slope factor. So that's, so say, determined by the order in which the labels appear here. If you had a third label listed before the vertical bar symbol, then that would be a quadratic growth factor automatically in Mplus. Next, we list the 3 outcome variables that refer to the 3 different measurement occasions, y1 through y3. So for example, the repeatedly measured anxiety or memory scores. And then the at keyword is used to then define the time scores that at which times those observations took place. So we write at and then t1 through t3, so that Mplus will take into account the proper time metric that was measured here. So that's it. So then Mplus will fit a linear growth curve model in this case, because we listed only 2 factors here on the left hand side of the vertical bar symbol, and Mplus will then fit a linear growth curve model using these time scores here. In this analysis we had 716 cases. You can see the y variables were the continuous indicators of the intercept and slope latent factors, and the time score variables served as variables with special functions here. Mplus gives us descriptive statistics in the same way as it would give them when we have a regular growth curve model with equal spacing of time between individuals. And so here we get the means. You can see that there was a decline in the means across time from about 50.5 at time 1 down to 48.9 around at time point 3. And we get the covariance matrix and the correlation matrix as usual, as well as univariate sample statistics. The fit statistics here include only information criteria and the log likelihood value. So an overall chi-square test is not available with type equals random in Mplus. So when you compare different models, or when you want to find out which model you should select, then in this case you could only use the information criteria to compare different models, for example a random intercept only model to a linear growth curve model, or the linear growth curve model to a quadratic growth curve model. You could take a look, for example, at the AIC values for those different models for the same data set, and then pick the model that has the smallest AIC value. Next are the unstandardized parameter estimates given under model results, where we find the covariance between the intercept and the slope factor. You can see it's negative and statistically significant in this case. So initially higher scores, so say were higher scores on memory were associated with stronger declines here in memory performance. So say the greater the initial memory performance, the lower or the more negative the decline in this example here. This is not necessarily realistic, but that's so say how those data here were generated. And then we have a mean of the intercept factor estimated, so that's the initial true value, and the slope factor mean is also estimated, which gives us the average decline in memory performance or anxiety or whatever you were measuring here per unit of time. Also estimated are the variances of the intercept and slope factors as usual, and the residual variances for the observed variables. So that's how you can include individually varying times of observations in a growth curve model when using wide format data. Another option in Mplus would be to use multi-level modeling or random coefficient regression analysis, which can also easily accommodate individually varying times of observation, where you have just long format data and you have a single column that indicates your time variable, and then that could be estimated as a random coefficient regression or multi-level regression model as well. I hope you found this video useful to learn more about growth curve modeling in Mplus with individually varying times of observations. If you did, then please subscribe to this channel, hit the like button, and check out the description for additional free resources, and I'll see you next time.